Here's the punctuated version of your text. At first, there was a vastly thick mass of issue. This mass went through a blast that brought about the arrangement of particles, atoms, stars, and worlds that we can notice today. For many years, this has been the clarification presented by physicists. Anyway, later research has presented a new viewpoint that recommends the universe doesn't have as early a beginning as initially accepted. Rather, it could be part of a repetitive cycle in which the universe goes through a progression of cycles of development and compression, perhaps in an endless circle. Brian Cox, a prestigious physicist, feels somewhat unsure about the theory of the universe's origin, contending that something can't emerge from nothing. This scrutinizing adds a fascinating component to the conversation. Moreover, research from the James Webb Telescope has uncovered data that goes against the possibility that the huge explosion denoted unquestionably the start of the universe. This prompts the essential question: if the enormous detonation was not the start of the universe, then what was? Join us on this excursion to the beginnings of the universe, where we will investigate the wildernesses of the huge explosion and answer this inquiry and more. If you are keen on keeping up to date with news about the universe and its surroundings, subscribe to our channel, hit the like button, share this video to reach more people, and turn on the notification bell. Researchers have fostered a detailed comprehension of the universe in its earliest stages, known as the theory of the prehistoric cosmic detonation. According to this model, the universe was a lot more modest, hotter, and denser than it is today, roughly 13.8 billion years ago. During that period, every one of the components that make up our reality were formed in a matter of minutes. In this hypothesis, our universe, including stars and galaxies, was once pretty much as minuscule as a peach and had an extremely high temperature of over a quadrillion degrees. Strangely, this shocking story aligns consistently with all current observations. Astronomers have explored everything from the remnants of electromagnetic radiation of the early universe to the abundance of the lightest components and have found that everything concurs with the expectations of the Big Bang to the best of our knowledge. This description fits the reality of our universe impeccably. However, regardless of its apparent power, we know that the theory of the universe's origin isn't the total picture. There's a missing part of this riddle, and that part is an understanding of the very first moments of the universe. This challenge is due in large part to the limitations of the physical theories we currently use. The combination of general relativity and high-energy particle physics provides us with a significant theoretical framework. However, as we dive deeper into the early moments of the universe, the mathematical complexity increases dramatically, reaching a point where our current methods cannot provide meaningful solutions. One of the hallmarks of this difficulty is the presence of a singularity, a point of infinite density at the start of the Big Bang. This idea suggests that the universe was once packed into an infinitely small and dense state, which seems unreasonable. To address this challenge, we need to explore new frontiers in physics, develop approaches that overcome these limitations, and provide a more complete understanding of the initial occurrence of the universe. Our current tools and theoretical frameworks are not robust enough to tackle this challenge, so we need to develop new physics that can incorporate and explain gravity and the other fundamental forces at extremely high energies. This is precisely where string theory comes into the picture. This theory attempts to be a physical model capable of unifying gravity with the other fundamental forces, especially at ultra-high energies. Essentially, string theory posits that it can provide an explanation for the first moments of the universe. Within string theory arises the concept of an eteric universe, which takes its name from the Greek word meaning a design or a fire. This idea proposes that the Big Bang as we know it was the result of a prior event, implying that it was not the absolute start but rather part of an ongoing process. Extending the concept of an eteric universe has led to the development of a related theory called cyclic cosmology. Although the idea of a cyclic universe has been considered for centuries, string theory provides a solid mathematical foundation for this conception. In the framework of cyclic cosmology, the universe functions as though it endlessly oscillates between big bangs and collapses in an eternal cycle that extends vastly into the past and future. This hypothesis of cyclic cosmology was proposed by the renowned physicist Roger Penrose, who was awarded the Nobel Prize. Penrose was intrigued by a remarkable mathematical relationship between the early universe, characterized by extreme density, heat, and smallness during the Big Bang, and the future state of the universe, which is described as very cold, extended, and devoid of matter. The hypothesis suggests that these two states become mathematically indistinguishable when pushed to their extremes. Although it might seem perplexing, the total absence of matter could be the driving force behind the creation of all the matter we observe. According to this viewpoint, the Big Bang originates from what remains almost subtly after all the matter in the universe has been consumed by black holes that eventually evaporate into dispersed photons in a vast void. The universe emerges from what, from another perspective, essentially approaches nothingness, although this nothingness is still a form of something, a physical universe, albeit an empty one. The mystery lies in how the same state can be interpreted as both a cold void universe and a dense universe, depending on the perspective. The key to this understanding lies in a complex mathematical method called the conformal change, which is a mathematical transformation that changes the size of an object while preserving its shape. Roger Penrose demonstrated that the void state and the hot, dense state can be connected through this scale change, adjusting their spatiotemporal patterns despite their differences in size. However, Penrose argues that the concept of size loses its significance under these extreme states of being. In cyclic cosmology, the sequence of events progresses from an old, cold state to a young, hot state. The presence of the hot and dense state is the result of the previous cold and void state. However, this causal relationship does not follow the usual pattern of time. As in these extreme states, both size and time lose their conventional meanings. The cold, void state and the hot, dense state exist on separate timelines, which means that from the perspective of an observer within his own time span, the cold, empty state would continue indefinitely. Physics and theory are intertwined in this domain of cyclic cosmology. While cosmology provides theoretical and detailed explanations for the origins of these cycles, whether Penrose's ideas gain support in cosmological advances, a deeper philosophical question still lingers about the origin of physical reality itself. How did these cycles come into existence? This leads us to contemplate the justification for the existence of something rather than nothing, which is one of the fundamental philosophical inquiries. For our purposes, we will focus on explanations within the realm of physics. There are three possible outcomes to consider in exploring the origins of these cycles. First, there might be no obvious reason at all. Second, there could be an infinite series of cycles where each cycle represents a different universe, and the initial quantum condition of each universe is somehow determined by some aspect of the preceding universe. Finally, there is the possibility of a single cycle in a repeating universe, where the beginning of the cycle is explained by some aspect of its own end. These possible outcomes are intriguing because they avoid the need for uncaused events and provide a more complex explanation within the physical framework. Penrose proposes the possibility of a perpetual succession of cycles influenced by his understanding of quantum mechanics. In quantum mechanics, a physical system exists in multiple states simultaneously until it is observed, at which point it randomly collapses into a single state. Penrose suggests that each cycle is influenced by random quantum events that give rise to variations between cycles. This idea opens up promising possibilities for experimental physicists, as it suggests the potential for detecting subtle traces or anomalies in the residual radiation of the Big Bang. The investigation of cosmology and the origins of the universe continues to captivate scientific inquiry, pushing the limits of our understanding beyond the natural domains of physics and into the speculative frontiers of theoretical frameworks. At the core of these inquiries lies the quest to unravel the mysteries surrounding the very origin of existence itself. How did the universe emerge, and what processes governed its evolution from inception to its current state? One of the enduring ideas that have captivated cosmologists is the concept of the multiverse hypothesis. This hypothesis posits that our universe is merely one of an infinite number of universes existing simultaneously, each with its own unique physical laws and properties. The multiverse hypothesis arises from the framework of quantum mechanics and inflationary cosmology, suggesting that during the rapid expansion of the early universe, pockets of spacetime could have undergone independent expansions, leading to the formation of distinct universes with varying characteristics. Inflationary cosmology itself has been a cornerstone of modern cosmological theories, providing a compelling explanation for the large-scale structure of the universe and the uniformity of cosmic microwave background radiation observed today. According to the inflationary hypothesis, a brief period of dramatic expansion, often referred to as cosmic inflation, occurred within a fraction of a second after the Big Bang. This rapid expansion stretched the fabric of space-time, smoothing out irregularities and setting the stage for the formation of galaxies and other cosmic structures. While inflationary cosmology has successfully addressed many observational puzzles, such as the horizon problem and the flatness problem, it also raises intriguing questions about the nature of the universe when inflation ends. Some theories propose that inflation could be eternal, with new universes constantly arising from quantum fluctuations within an ever-expanding multiverse. This idea challenges conventional notions of a single, linear cosmological history and invites speculation about the broader implications of an infinite and ever-changing cosmic landscape. Moreover, the concept of dark matter and dark energy continues to intrigue cosmologists. Dark matter, inferred from its gravitational effects on visible matter, suggests the presence of a type of matter distinct from the ordinary matter that constitutes stars, planets, and galaxies. Its gravitational influence plays a crucial role in shaping the large-scale structure of the universe. On the other hand, dark energy is believed to be responsible for the accelerated expansion of the universe observed in recent astronomical surveys, such as those measuring the distances of supernovae. This mysterious force counteracts the gravitational pull of matter, driving galaxies apart at an accelerating rate. The nature of dark energy remains one of the most pressing questions in cosmology, with implications for the ultimate fate of the universe, whether it will continue to expand indefinitely or eventually collapse or transition into another phase. Cosmologists also grapple with the concept of cosmic microwave background, CMB, radiation, which serves as a remnant of the early universe. Originating from a time roughly 380,000 years after the Big Bang, detailed measurements of the CMB have provided significant insights into the composition, age, and structure of the universe. Tiny fluctuations in the CMB temperature across the sky offer a glimpse into the seeds of structure formation, providing evidence that the universe began as a hot, dense state and gradually evolved into the complex cosmic tapestry we observe today. Beyond observational astronomy, theoretical physics continues to explore ambitious frameworks such as M-theory and quantum gravity, aiming to unify the fundamental forces of nature and reconcile the principles of general relativity with those of quantum mechanics. M-theory, an extension of string theory, posits that the universe may consist of higher dimensional structures known as branes, offering a potential resolution to long-standing puzzles in particle physics and cosmology. Quantum gravity, on the other hand, seeks to describe gravitational interactions at the quantum scale, where conventional notions of reality break down. This field of research remains highly theoretical, with implications for understanding the behavior of black holes, the early universe, and the fundamental nature of reality itself. The quest for a complete theory of everything, a framework that encompasses all known physical phenomena within a single coherent structure, remains a central objective of modern theoretical physics. Such a theory would not only unify the forces of nature, but also provide deeper insights into the origins and evolution of the universe, from the smallest subatomic particles to the vast cosmic structures spanning billions of light-years. Philosophical inquiries into cosmology also raise profound questions about the nature of existence and our place within the universe. The anthropic principle, which posits that the universe's physical constants and conditions are finely tuned to support the emergence of intelligent life, invites speculation about whether the universe was designed with a purpose or if our reality is a fortunate outcome of cosmic evolution. The study of cosmology intersects with broader philosophical debates about determinism versus free will, the nature of causality, and the possibility of multiple universes with different physical laws. These discussions reflect humanity's enduring curiosity about the origins of the universe and our place within it, prompting reflections on the limits of scientific knowledge and the boundaries between the known and the unknown. In conclusion, cosmology stands at the intersection of observational research, theoretical exploration, and philosophical inquiry, offering a window into the fundamental nature of reality itself. From the origins of the Big Bang to the evolution of galaxies and the mysteries of dark matter and dark energy, cosmologists continue to push the boundaries of human understanding, striving to unravel the cosmic tapestry that surrounds us. As our tools and theories advance, so too does our appreciation for the vast complexity and beauty of the universe, inspiring wonder and curiosity in generations of scientists and philosophers alike.